Hi everybody. So in this video, we're going to look at the probability generating function for a Poisson binomial and geometric distribution. And if you want to work along with me, you can download a copy of this PDF from my website. I'll leave a link below. So in our first question, we've been told that X is distributed with a Poisson with a lambda or an average of 2. We've been asked to show from first principles that this is the probability generating function for this distribution. So because we've been asked to show from first principles that this is the probability generating function, we need to combine each of these three equations. We know that the probability generating function for a discrete random variable is the sum of the probabilities multiplied by t to the power of x. And we know the probability mass function for our Poisson model is given here. And we can use each of these. So if we substitute this mass function into our probability generating function, then we'll have the generating function of x in terms of t will be the sum of e to the minus lambda, and lambda is 2, so e to the negative 2, multiplied by 2 to the power of x over x factorial, and then this is multiplied by t to the x. So what we need to do, we can pull out this e to the negative 2 in front of the summation, because this is just a constant, and then we can let x equal 1, 2, and 3, and so on. So we'll get e to the negative 2, and then if we let x equal 0, we'll have 2 to the 0, which is 1, 0 factorial, which is 1, and t to the 0, which is 1. So this will just be 1. Then if we let x equal 1, we'll have 2 to the 1 over 1. So this will be 2 multiplied by t to the 1. So this will just be t. And we're adding these up as we go. If we let x equal 2, we'll get 2 squared times t squared. So I'm going to write this as 2t all squared over 2 factorial. And then if we let x equal 3, we'll have 2 cubed times t cubed, or 2t all cubed, over x factorial, so 3 factorial. What do you think the next term will be when x equals 4? So we'll have 2 to the 4 times t to the 4, or 2 to the t all raised to the power of 4, over 4 factorial, and this will carry on. But do you see a pattern here if we compare this to the Maclaurin expansion for e to the x? We can let this x equal 2t, and then we'll get exactly the same as we have in our expansion. So all of this bracket becomes e to the negative 2 multiplied by e to the 2t. And then we can use the rule of indices where we just add these two powers together. So this will be e to the 2t minus 2. We can factorize our power, so we get e to the 2 times t minus 1, which is exactly what we were asked to show here. Okay, let's try another question. Okay, so now we've been given that y is a discrete random variable which is distributed geometrically. And we've been asked to show from first principles. Now the probability generating function is given as this. So I've given you the formulae that you'll need here. Do you want to try this question yourself? You can pause the video and come back when you're ready. Okay, so welcome back if you had a go. So if we substitute this probability mass function for a geometric distribution into our generating function. So we'll get the generating function of y in terms of t will be the sum of p multiplied by 1 minus p to the y minus 1, put this in brackets, all multiplied by t to the y. Okay? And then because it's a geometric distribution, the lowest value of y we can have is 1. We get our first success on the first go. So when y equals 1, we'll have p multiplied by 1 minus p to be 1 take away 1. So all of this will become 1, and we're just left with p times t to the y. So this will just be pt. Then if we let y equals 2, we'll have the p, 1 minus p, to the power of 2 take away 1, times t squared. Then y equals 3, we'll have a p, 1 minus p to the 3 take away 1, times t cubed. Then we'll have our next term, when y equals 4, we'll have p, 1 minus p cubed to the t to the power of 4. And this will go on infinitely. So then you can see that we can factor out a p and a t from each of these terms. Then we've got the 1. We've taken this p and one of these t's out. So we've got 1 minus p times t, that's left. We've taken out this p and one of these t's. So we've got 1 minus p times e squared left. And the next one, 1 minus p times t cubed, and so on. Now, can you see what's happening here? We've got a geometric series where the common ratio, our r, is t times 1 minus p. And because p the probability, we're looking at a convergent series to infinity. So we can use this equation to simplify the summation. We know that a is our first term, which is 1, and we know that r, the common ratio, is t lots of 1 minus p. So we can substitute these values into here. So the generating function of y in terms of t will be the pt multiplied by a over 1 minus r, which is t times 1 minus p. And then we can multiply these together and we get the probability generating function in terms of t for y will be pt over 1 minus p times t. Okay? And this is what we were asked to show here. Let's try one more question. Okay, so in our final example, we're given that w is a discrete random variable such that it's distributed binomially. We've been asked to show from first principles that this is the probability generating function for this distribution. Again, do you want to try this question yourself using these formulae? You can pause the video and come back when you're ready. Okay, so how did you get on with that? If we substitute this probability mass function into our probability generating function, then we'll have generating function of w in terms of t will be the sum of n choice w multiplied by p to the w multiplied by 1 minus p to the n minus w, all multiplied by t to the x. Sorry, t to the w. Okay? And then because we're looking at a binomial, the lowest value of w we can have is 0. So a generating function of w, when w equals 0, will have n choice 0, which is 1, p to the 0, which is 1, and then 1 minus p to the n minus 0, which is 1 minus p to the n, times t to the 0, which is 1, plus when w equals 1, we'll have n choice w, so n choice 1. Actually, here I should also have written n choice 0. We'll see why when this tidies up later. So we've got n choice 1 of p to the 1. I'm going to leave this power as 1 in, times 1 minus p to the n minus 1 times p to the 1. Okay? And then when w equals 2, we've got n choice 2 of p squared 1 minus p to the n minus 2 times t squared. And then when w equals 3, we'll have n choice 3 of p cubed multiplied by 1 minus p to the n minus 3 of t cubed. Okay? And this would carry on. So what we can do here, because we've got p squared and t squared, p cubed and t cubed, we can tidy this up. So we've got n choice 0 of tp to the 0 times 1 minus p to the n plus n choice 1 of tp to the 1 times 1 minus p to the n minus 1 plus n choice 2 of tp squared multiplied by 1 minus p to the n minus 2. And then finally, n choice 3 tp cubed times 1 minus p to the n minus 3. So then, can you see that this series is exactly the same as what we have here, where the a would be the 1 minus p. You can see this is raised to the n, as is the 1 minus p. And the b would be the tp. So tp to the 0, which is here, tp to the 1. So a b would be tp, and the a would be 1 minus p. So we can simplify our summation. So the generating function for w in terms of t would be a 1 minus p plus b tp to the power of n. And that is what we have here. Okay? Well, thank you very much for watching. I hope you found that useful. If you did find that helpful, please like and subscribe, and you can download the full lesson and the PDF that accompanies this video from my website, mrmathematics.com. I'll leave a link below.